And our next speaker will be Nina Petrova. She has been working with Mike Edmonds since 2000 as a full-time researcher, and most of her research has been on the Charcot. So I think most of us have read some of her beautiful publications on this topic. So Nina, I'm looking forward to hear from you.
Good morning, everyone. I have a lovely title, actually, a Charcot, a riddle inside an enigma wrapped in edema. And I would also like to acknowledge funding from Diabetes Research and Wellness Foundation for supporting my research. So the Charcot riddle is really peculiar. And in the Charcot riddle, we have no signs, and we also have no time. Initial X-ray may be normal, but 10 days later you can see the severe metatarsal-tarsal dislocation. And this is also confirmed on this lateral X-ray, where you can see the bone destruction and the foot deformity. So we have a red-hot swollen foot with early evidence of bone resorption, which can lead to bone and joint fragmentation. And I believe in the Charcot riddle, the enigma is this pathological bone destruction which is wrapped with inflammation. Can we measure inflammation? We tried, and it is important to know that there is a dissociation between all these local signs of inflammation but lack of systemic response. It is a severe bone destruction with osteolysis, as you can see on this X-ray. And one can compare this only with the fall from a 9-story tower block, if you can survive that, as referenced in the Metro, which is the most written newspaper in London. Everyone can get this free reference from the tube. But in our patients, this severe osteolysis occurs only simply by walking, because of neuropathy. And for those of you who've seen this slide yesterday, I just want to mention that Charcot medicine is a subspecialty of the neuropathic medicine, and in this condition we have no signs, no symptoms and signs, no investigations, no diagnosis, no treatment, and patients present to us with foot deformity and also bone destruction. And you can see this extent of bone destruction in this CT reconstruction scan. And not only that, but you can see also the vascular calcification. This can also be noted on a lateral foot and ankle X-ray, as shown here. And why is it important? And I would really like to refer to Professor Jeffcoat's question, is the Rankel the missing link linking vascular calcification and osteolysis in diabetic neuropathy? And the Rankel OPG signaling pathway is being important, and it is modulated by neuropathy, as shown here. We have a lack of CGRP, and perhaps it is important and leads to osteoclastic differentiation and increased bone resorption in the bone, whereas in contrast, in arteries we have increased osteoblastic differentiation and deposition of mineralized matrix. We have now clear evidence coming from Manchester, from Professor Bolton's group, that indeed the Rankel OPG signaling pathway mediates a medial arterial calcification in diabetic Charcot neuroarthropathy. But does it play a role in bone? We have been working over the last years on a hypothesis. We hypothesized that the activated osteoclasts play a key role in the pathological bone destruction of the active Charcot foot. Osteoclasts are the principal bone resorbing cells, and osteoclastic precursors circulate in the monocytic fraction of blood, and they're regulated by the Rankel and OPG signaling pathway. And we've been particularly interested to find out the role of this cytokine in osteoclastogenesis in acute Charcot osteoarthropathy. inactive Charcot osteoarthropathy. And one can study osteoclastic activation with an in vitro assay. And as I mentioned, osteoclastic precursors circulate in the blood. And what we did, this is a summary of our experiment. So we took blood, and then after centrifugation, we isolated osteoclastic precursors, which are mononuclear cells. And then we initially cultured them with macrophage colony stimulating factor, which is a survival factor for these cells, just to keep them alive. And then we added Rankel, a classical osteoclastic activator, and then we looked for osteoclast formation on culture plates. And to assess the functional ability of these cells to carry out bone resorption, we also cultured them on bovine discs. And to confirm that Rankel plays a role, we added Rankel at day 7. And to confirm that it's indeed the osteoclastic driver, we also added OPG to see whether we can inhibit the response to Rankel. So we cultured mononuclear cells for 17 days, and then we counted the number of TRAP-positive multinucleated newly formed osteoclasts on 24 plates. And this is a picture of a bovine disc resorbed by newly formed osteoclasts. And you can see these pits, which have different shapes, and we quantitated this by image analysis. And here is an example of a resorbed bone disc with a 6 millimeter diameter, and we carried out and we analyzed it, and we calculated the area of resorption on the surface as percentage area resorbed. We studied 10 patients with acute active Charcot foot, diabetic patients, and healthy control subjects. And what we did, we compared the number of newly formed osteoclasts and also the area of resorption on bovine discs in 3 culture conditions, only with MCSF, so this was our negative control culture, after stimulation with Rankel, and after that, after inhibition of OPG. So this slide shows examples, typical examples in a Charcot patient, patients with diabetes and a healthy control. And as expected, when we cultured cells only with MCSF, we had no osteoclast formation. The addition of Rankel on the second row showed multiple newly formed osteoclasts in the 3 groups, and osteoclastic formation was inhibited after the addition of OPG. We then assessed osteoclast resorption. Again, no resorption in the MCSF cultures as expected. Multiple resorption pits after celluloid blue staining on the second row, and this resorption was inhibited after the addition of OPG. So what about this stimulation with Rankel? So interestingly, we didn't find any difference in the osteoclast formation. As you can see, the newly formed osteoclast between the 3 groups looks quite similar, but there was definitely a difference on the resorbed surfaces that we examined. And indeed, between the 3 groups, there was no difference in the number of newly formed osteoclasts, but when we compared the area of resorption on the surface of these resorbed discs, this was significant. It was significantly increased in the Charcot compared with the diabetic patients, and also in the Charcot compared with the control subjects. So increased response to Rankel. These observations confirmed our preliminary observations that we published a few years ago. But what was really interesting is that when we looked at these resorption pits at a higher magnification, you can see that the resorbed disc between people with diabetes and controls did not look that similar. The majority of the pits looked like single resorption events, in contrast to the multiple, multi-shaped erosions that we noted in the Charcot cultures. And it is well established that the osteoclastic culture assay has some limitations because it only assesses resorption as expression of percentage of eroded surface, and does not really take into consideration the differences between the different pits, whether they're pits or trenches, and it doesn't take into consideration their depth and also erosion profile. So then we asked the next question, do the osteoclasts that we generate from Charcot patients, do they have different resorbing activity? And is there any difference in the resorption pit profile between Charcot patients and controls? And we really wanted to find out whether we can measure these Grand Canyons of osteoclastic resorption in this condition. And in order to do this, we used a novel technique. We used a surface profilometry, which is actually not new. It's used in material science, and it is used to measure the roughness of surface. And as you can see, this is the technique that we use. The resorb disc, which were on a glass slide, were placed on the stage. And then this technique has a stylus, which is very thin. It is 2.5 micrometers. It was lowered, as shown in the picture in the middle, at the lower row. And then the stylus is dragged along the surface of the disc, and it can graphically represent the erosion profile. So here is me in the thin film technology laboratory in Imperial College, where I had the access of this technique. And as you can see, one can observe the surface of the resorb disc due to the integrated camera with the profilometer. And you can see the surface of the disc on the monitor on my right. And here is an example of a non-resorb disc in MCSF-treated cultures. As you can see, it looks rather smooth. And in the MCSF and Rankel-treated cultures, we see all these little black dots which correspond to the resorption areas. So this is the comparison to Lydian blue staining of resorb disc at the top line, and then images with resorb bone disc taken with the integrated camera of the profilometer. Can I have the video, please? And I would really like to show you this technique. So you can see the stylus and the resorb disc. And initially, we started the measurement away from a non-resorb surface in order to have the zero level. And then the stylus followed the pattern of erosion and then graphically reproduced the eroded profile and the profile of the disc. We compared the erosion profile between the different culture conditions, and as expected in the MCSF cultures, there was no resorption. The surface of the disc was it was very smooth, as shown by the blue line in the three groups in the Charcot diabetic group in control and control subject. But you can see these really deep eroded surfaces which graphically represented the erosion profile in the MCSF and Rankel-treated cultures. And these erosions were also inhibited after the addition of OPG, as shown by a straight line, green line on this graph. When we compared the different erosion profiles between the three groups, we interestingly noted that there was quite a substantial difference. In the Charcot patients, the eroded cultures, the eroded disc, presented with these extensive erosions below the surface, as shown on this slide with the blue line, and there was no difference between cultures from diabetic patients and also controls. And when we compared the area of resorption under the surface, that was significantly greater in Charcot patients compared with diabetes controls, with diabetic patients, and also with healthy controls. So in the MCSF and Rankel-treated cultures, we had this extensive response to Rankel by newly derived osteoclasts from Charcot patients, and this activity was blocked by OPG, confirming the role of this cytokine in the pathogenesis of osteoclastogenesis. But what about my second variable from the riddle, the inflammation? Does it really play a role? I would really like to acknowledge Professor Jeffcoat with putting forward a fantastic hypothesis about the possible role of pro-inflammatory cytokines in the cause of neuropathic inflammatory osteoarthropathy. And why cytokines are important? It has been shown that they have a synergistic action on osteoclasts, And they increase production of Rankel by stromal cells, but they also have a direct action on osteoclastic precursors. And the rate of osteoclastogenesis in vivo is equal to the sum of activating signals and inhibitory signals. So we have a really complex equation. And we have been particularly interested in the role of TNF-alpha as a modulator of this activity. And indeed, this was our next question. Does TNF-alpha modulate the response to Rankel activation in acute Charcot osteoarthropathy? And to find out, we used the same experimental model, only with the addition that we added neutralizing antibodies to TNF-alpha to block any possible TNF-alpha mediated effect on osteoclastic precursors. And again, we compared osteoclast formation and resorption between the three study groups. TNF-alpha had no effect on osteoclast formation, and that was noted in the three groups of patients, so there was no significant difference in the number of newly formed osteoclasts after the addition of TNF-alpha, after inhibition of TNF-alpha. Inhibition of TNF-alpha also did not lead to any changes in osteoclastic resorption in people with diabetes and in healthy controls, but interestingly, it led to a significant reduction in the extent of bone resorption that we noted on bovine bone discs. As you can see, all these trenches and lacunae, they looked completely different after inhibition of TNF-alpha. And when we compared the area of resorption, indeed, we noted a significant reduction in the area of resorption under the surface in Charcot, and that was unchanged in people with diabetes and healthy controls. Furthermore, addition of anti-TNF-alpha did not lead to any changes in the erosion profile in people with diabetes and in healthy controls. But interestingly, if you look at the top plot, you would see that all these extensive resorptions that we noted in the MCSF and Rankel treated cultures in Charcot patients, presented here with blue, were reversed after the addition of anti-TNF, as shown in red. And here is an example, the comparison between the three groups: extensive resorption under the surface in MCSF and Rankel treated cultures, and that was normalized after inhibition of TNF-alpha. And there was also significant reduction of the area of the resorption under the surface in Charcot cultures. One other interesting finding is that we noted that there was a difference in the pit morphology. As you can see in diabetes and in control subjects, the pits usually look like round, they had a round shape, whereas in the Charcot patients we had these extensive lacunae which were reversed after inhibition of TNF-alpha. And in order to quantitate this, we really looked into the graphical representation of the erosion profile, and we measured pit morphology. And we tried to group the different types of pits that we noted into pits presenting as a single erosion under the surface, and we call these unidented pits. And the pits with more than 2 dents under the surface, we call them bidented pits, and with 3 or more dents, we call them multidented pits. And we also measured their dimension at the surface, at the width at the surface, the forward at half maximum, and also the maximum depth. I can tell you that was a lot of calculations, but I think it was worth doing it, because what we really noted is that there was a difference in the proportion of pit distribution between the different culture conditions. And what was really interesting, that more than 40% of the pits in the MCSF and Rankel treated cultures presented as multidented pits, and after the addition of anti-TNF, this was significantly reduced to 25%. And also, interestingly, there was also a switch between the presence of unidented pits, less frequently seen in the MCSF and Rankel treated cultures, and more frequently seen after inhibition of TNF-alpha. And I'm sure that you would all agree that there is quite a significant difference between the two pictures of the resorbed bone discs at the bottom. In contrast, inhibition to TNF-alpha did not lead to any changes in the pit distribution, and that was only noted in the Charcot cultures. So what would this really mean? I think osteoclastic behavior is very interesting. So the osteoclast is an interesting cell that will stuck to the bone, resorb and move, resorb and move. So it has a specific behavior, and this is the so-called intermittent way of bone resorption. But what we really noted in the presence of TNF-alpha, our osteoclasts were demonstrated continuous mode of resorption. So instead of migrating, they were chewing the bone, and this resulted in these deep, multidented pits, and these were significantly greater both at the surface and under the surface. And then the inhibition of TNF-alpha, as shown on the lower level of the graph, reversed this abnormal behavior, and then we more frequently saw intermittent mode of resorption. And perhaps, although these studies will not fully show what is the riddle inside the Charcot foot, perhaps what they might have shown is that we have trauma, which leads to inflammation and fracture, and there is increase and this leads to upregulation of TNF-alpha and Rankel. And TNF-alpha is known that it can inflammatory activate the endothelium, and this may lead to this increased recruitment of circulating osteoclastic precursors. Furthermore, TNF-alpha is known that it may have led to increased survival of these newly formed osteoclasts and reduce apoptosis, and this is why they may have been able to stay in this continuous mode of resorption, and therefore this may all have led to increased osteoclastic activity and Charcot osteoarthropathy. So to summarize the second part of our experiments, what we noted was that the addition of anti-TNF-alpha resulted in significant reduction in the area of resorption on bovine bone discs, both on the surface and also under the surface. And furthermore, inhibition of TNF-alpha reversed the pathological erosion profile and pit morphology that we noted in the Charcot cultures. And one of the main findings of this work is that we really try to introduce two novel approaches to the investigation of the Charcot foot, namely the osteoclastic culture assay and also surface profilometry. And from this work, we hope we have been able to demonstrate that Rankel is the main osteoclastic activator, and that the pro-inflammatory cytokine TNF-alpha modulates Rankel-mediated osteoclastic activity and also osteoclastic behavior. But the limitation to this study is that we actually did not study any driving mechanisms, and it is possible that this enhanced resorbing activity in MCS7 Rankel-treated cultures could be due to cathepsin K upregulation. So now I'm introducing a new player. And what is cathepsin K? Well, this is the main lysosomal collagenase, which is responsible for degradation of type 1 collagen. And it has been also found that the extent of resorption over bone surfaces results from balance between factors that upregulate or downregulate cathepsin K. Now there is experimental work that have shown that if we have cathepsin K upregulation, we more frequently see continuous resorptions, more trenches, what we saw in the MCS7 Rankel-treated cultures in our Charcot patients. But if we inhibit cathepsin K, we have intermittent resorption, and we see unidented pits or single resorption events. Both TNF-alpha and Rankel are known to upregulate cathepsin K. However, the role of cathepsin K in Charcot osteoarthropathy is unknown. And instead of finishing with a take-home message, I'll finish with a take-home question. And I would really like to ask the question, can cathepsin K upregulation solve the riddle inside the enigma of bone destruction wrapped in edema? And to conclude, I would really like to finish with the epilogue from Charcot, who advised us, let us keep looking in spite of everything, let us keep searching, and it is indeed the best method for finding, and perhaps, thanks to our efforts, the verdicts we give our patients tomorrow will not be the same as we much give him today. Thank you very much.